Everyone, welcome to CSM walkthroughs. I'm Ashley, and today I'll be walking through Heaps today. And Heaps consists of two parts. The first part is a conceptual question about Heaps, and the second part is walking through the different processes that use Heap, such as heapification, insertion, and removal. So before we start, I want to go over what exactly is a heap. So heap is a binary tree that fulfills two conditions. First of all, it's complete. So what that means is it's only missing elements at its bottommost layer, if any at all. And for example, this tree would be complete because it's only the only element it's missing is would be the bottom right here, and since that is in order of left to right, top to bottom, that means it fulfills the completeness category. And the second one is a heap is defined by its fulfillment of heap property. So what that means is for a max heap, that means all the numbers for a node, all the numbers below it have a value of that is less than or equal to its value. So every single value in the level that it has its children will be less than or equal to. And the mean heap, the opposite is true. So for every node, its children would have a value greater than or equal to it. So the first question asks us, there are 4 ways to heapify, and which 2 ways actually work. And it gives us 4 methods: level order bubble up, level order bubble down, reverse level order bubble up, and reverse level order bubble down. So I guess the best way to figure out which ones actually work is to walk through the different methods. So let's walk through the first one, level order bubble up. So what that means is that we traverse the tree in level order, so from top to bottom, left to right. And then if we see something that violates the heap property or like the heap definition, we will bubble it up. And just to be clear, for this example, I will be executing this on min heap. I'll be trying to create a min heap from these values, though you can also try to do it with max heap. Okay, so let's start. So basically, if we're going level order, we would start with the top level. So 14, there's nothing above it, so there's nothing to bubble up, so we can move on. Move on to 4. And now we want to check if 4 is less than 14. 4 is less than 14. So in order to make it closer to the min heap, we want to bubble it up. So I want to switch, put 14 here and put 4 here. And after 4 bubbles up here, that means it's at the top now and there's nothing else to bubble up, so it stops. And then let's go on to 11. We're checking if 11 is greater than 4. 11 is greater than 4, so it stays here. And now we go on to the next level, which is 2. Check if 2 is less than 14. It is. So 14 moves down here, 2 moves up here. And check if 2 is less than 4. That is true. So 4 gets moved down here, 2 gets moved up here. And then we do the same with 3. 3, we should compare 3 and 4. 3 is smaller, so they swap. And 3 and 2, 3 is larger, so it stays. And then we do 10 and 11. And 11 goes down and 10 goes up. So yeah, let's draw out the resulting tree. So it would be 3, 2, 2 on top, 3 and 10 as its children, and 14 and 4 as 3 children. So let's check. So 3 and 10 are 2 children, and they're both greater. 3 has 2 children, 4 and 14, and they're both value greater than 3. So we successfully created a min heap. So that means that level order bubbling up actually works. So let's move on to the next method, level order bubbling down. So we still traverse the tree in level order, so top to bottom, left to right. Instead, when we see a disruption, we want to bubble it down. So we want to check it with its child instead of checking with its parent. So the first thing we want to do is start with 14. We compare 14 to a children, or 11. It's smaller than, it's greater than both of them. So it chooses this, and we're trying to create a min heap. So choose a smaller one. So choose creates so search 4, moves down, and then compare 14 with 2 and 3. It's greater than both of them. 2 is a smaller one, so it swaps. 14 is down here, 2 is up here. And that's what we have. And then now we go to the next node, so it's 2. And we try compare 2 with 14, 3. 2 is smaller than it, so it stays. Then we go to 11. 11 is greater than 10, so we switch. And then we at the bottom layer, just nothing to bubble down because they have no children. So let's draw the resulting tree of this. And the thing is, if we look at it, it is not actually a min heap, because if you compare 4 to a children to 10, 2 is less than 4, so it does not satisfy the heap property. As a result, we know level ordered bubbling down does not work. So now let's move on to reverse level order bubbling up. So for reverse level order, we want to traverse right to left, lowest level to top level. We're bubbling up like as we did before. So so we start with 10 and then compare 10 to 11. They are different. So we swap it up, 10 to 14. They're different. It fulfills the min heat property, so bubble up. That's what we have. And then now we go to 3. 3 is less than 4. Swap. 3 is less than 10. Swap. And then I'll do 2 compared to 10. 2 is less than 10, so they swap. 2 is less than 3, so it swaps. And yeah, so that's how you would go in reverse order bubbling up. Let's draw the resulting tree. So 3, 14, 10, 4, 11. So let's check if this is a valid min heap. So 2 is less than 3 and 14. That's correct. 3 is less than 10 and 4. That's correct. But 14 is not less than 11. So that violates the heap property. So that means we know that our reverse level order up does not fulfill the heap properties and will not create a correct heap. So now let's move on to the last possible way, reverse level order down. So we'd still be going right to left, bottom to top, except we'd be bubbling down as we did before. So the first layer, they're at the bottom most, so there's nothing rubbed down. And then we go to, so we can go to 11. So we checked 11 and 10. 11 is greater than 10, so we swap them. And then and then it reaches bottom, so it stops bubbling. Then we go to 4. 4 compares to 2 and 3. 4 is greater than 2 and 3, so we can swap it. And that's how we get the swap. And then we move on to 14. 14 compares to 2 and 10. 14 is greater than it, so we swap it 2 because 2 is smaller. We have 14 here. We do compare 14, keep bubbling down 14. 14 is greater than 4 and 3. So we swap it, and then 14. And yeah, so here's the resulting heap. And we can quickly run through the heap properties to see if it's correct. So it is complete. And let's compare the values. So 2 is less than 3 and 10. That's correct. 3 is less than 4 and 14. That's correct. And 10 is less than 11. That is correct. So that fulfills all the properties of a heap, min heap, and that means reverse order of order bubbling downwards. So the two methods actually work. If you want to heapify, are using level order bubbling up, reverse order bubbling down. So hopefully that makes sense. And now let's move on to the second part of the problem. So for part A, we want to show the heapification of a tree, and we want to create a min heap of it. So I redrew the tree down here for our convenience. And since we already have practice heapifying min heaps, we'd be able to apply the things we learned from the previous one here. So we learned that level order bubbling up and reverse order bubbling down both result in the correct heap. So either will work, but I will be using reverse level order bubbling down today. So we start by on the bottom level. 8 is the bottom, has no children, cannot bubble down, could not bubble down, and we get to 7. So 7, we convert to 1 and 8. 7 is greater than 1, so we want to switch. So 7 becomes this, 7 plus 1, 7, and 1 becomes 7, so these switch spaces. 7 reaches the bottom, there's nothing, and then 7 reaches the bottom, and then there's nothing left to bubble down, so it stops. Then we convert to 6. Where 6 to 9 and 5. 5 is less than 6, so we swap it. So 5, 6, and that's what we get. And then we get to the top, which is 9. Compare 9 to 5 and 1. 9 is greater than both of them, so it's less than 1. And then we continue bubbling down because it's not reached the bottom yet. So we compare 9 to 7, 8, and it is greater, so we swap it. And yeah, so let's draw the heapification of the tree. So it would be 1, 5, 7, 9, 6, 9, 8. And if you look at it, it satisfies the properties of a bin heap. It is complete, and every value is smaller than its children. So yeah, that is how you heapify the tree. Now moving on to part B. Now I want to insert the value too. When inserting the value into the heap, you'd want to add it to the next possible spot. Since we have all the rows filled out, we want to insert the number 2 into the leftmost spot of the next layer, like that. And then we want to, after we insert it, we want to bump it up until it reaches its correct spot. So compare 2 and 9. 2 is less than 9, so they switch. And then compare 2 and 5. 2 is less than 5, so they switch. And then compare 2 and 1. 2 is not less than 1, so it stays there. So, and since 2 is the only thing we added to or modified the graph of, we don't need to check any of the other comparisons. We can just redraw the graph like that. We have 2, 7, 5, 6, 9, 9, 8. And if you look at this is a valid min heap. So that is how we can insert and not disrupt the heap properties. And to the last part of the problem, part C, we want to remove a value. And I'm going to copy this over. So in order to remove a value, you want to basically, you'd want to take the value and obviously cross it out or remove it from the heap, but you want to take the bottommost or the last node in, or what the last node in level order is, and you want to switch it and just automatically put it there at the top. And after you put it at the top, you want to bubble it down until it reaches the correct spot. Now for bubbling down, everything else should have shifted into place and replaced it as a valid min heap. So let's try it. So we put so we remove 1, so we take the last element, which is 9, and put it one spot at the top. And this violates a min heap because it's a large element at the top. So we need to bubble it down. So now we'll compare 9 to 2 and 7. 9 is greater than both of it, so we switch to 2. So 2, 9. And then we continue bubbling 9 down. 9 compares to 5 and 6. It is greater, so we switch it with 5. And so on. And this node spot does not exist anymore, so it doesn't need to swap again. So let's draw out what this looks like. So we have 2 here. Now we have 5, 7. 2 is smaller than 5 to 7. Okay. We have 5 connected 5 with 9 to 6. 5 is smaller than 9 to 6. That's correct. And then we have 7 connected to 9 and 8. So these two numbers are also correct. So it fulfills the heap property and it's complete, which means it is a valid min heap. So yeah, so those are how you heapify, insert, remove, and determine like what are heaps, like different heap operations. Hopefully that was helpful and see you guys next week.